Welcome everyone. Today we begin our diagnostic testing module. Diagnostic testing sits at the center of veterinary decision making, from a single animal in the clinic to regional surveillance and eradication campaigns. The problem is that we often treat a test result as if it were truth. In reality, a test result is evidence, and evidence has uncertainty. The job of epidemiology is to quantify that uncertainty so decisions are defensible. A diagnostic test is not good in isolation. It is good for a purpose: screening, confirmation, prevalence estimation, or policy action. The structure for the session follows the same logic you would use in practice. Start by defining what good performance means with sensitivity, specificity, and predictive values. Then anchor those definitions in the 2x2 table, the preferred tool of epidemiologists. Next comes the practical reality. Many diagnostic tests do not produce a simple positive or negative results. ELISA optical density, antibody titers, biochemical markers, these are continuous. A cutoff turns a continuous measure into a decision, and moving that cutoff changes sensitivity and specificity in opposite directions. That trade-off becomes the basis for receiver operating characteristic curve analysis and for deciding what optimal means.
Every diagnostic test evaluation starts with a comparison against what we call a gold standard. The gold standard represents the best available method for determining the true disease status of an animal, such as culture, necropsy, histopathology, or a well-validated PCR. Importantly, the gold standard defines the truth against which the new test is judged. However, a critical caveat must be stated early. Gold standards are rarely perfect. Culture may miss fastidious organisms. Necropsy findings can be subjective, and PCR may detect non-viable organisms. Errors in the gold standard directly affect the apparent performance of the test being evaluated. This is why diagnostic accuracy is always conditional on the reference method used. So the correct interpretation is: the new test is being evaluated against the best available truth proxy. That framing matters later when you consider disagreements.
Everything starts with the 2x2 table. Disease status is represented in the columns. Disease present and disease absent. The test result is represented in the rows. Test positive and test negative. The four central cells labeled A, B, C, D are the only counts you ever really need. A is true positives, B is false positives, C is false negatives, D is true negatives. The top row, A plus B, is the positive total. The bottom row, C plus D, is the negative total. The diseased column total is a plus C, and the non-diseased column total is B plus D. The overall population total, it's a plus B plus C plus D. Once this layout is stable in your mind, diagnostic calculations become mechanical rather than confusing. Most errors in diagnostic interpretation are not math errors. They are table layout errors by mixing up B and C or conditioning on the wrong margin.
Let's take an example to validate a new rapid ELISA for bovine viral diarrhea. Virus isolation is used as the reference method, gold standard. A sample is drawn from the population, the test is applied, animals are classified into test positive and test negative groups. Although the test might give wrong classification if the disease, the key is that the true disease status is derived from the reference method, gold standard. Not assumed. The study comprised 400 cattle by testing the same animals with both the new ELISA and the virus isolation and then compare results. We continue by putting the study data into the 2x2 format, total animals tested 400. Based on virus isolation, 100 are infected and 300 are not infected. The ELISA results distribute across the 4 cells. 95 in the true positive cell, 15 in the false positive cell, 5 in the false negative cell, and 285 in the true negative cell D. The raw totals confirm this. ELISA positive total is 110, ELISA negative total is 290. This table is doing more than storing numbers. It defines the interpretation of the ELISA. Every diagnostic metric is a probability defined by one margin of this table. If the objective is to evaluate how well the test finds disease, attention goes to the diseased column. If the objective is how trustworthy is a positive, attention goes to the test positive row. That shift in conditioning, columns versus rows, is the conceptual pivot between sensitivity, specificity, and predictive values. Sensitivity and specificity are often described as intrinsic test properties because, in theory, they do not change with prevalence. Sensitivity answers among truly diseased animals what fraction test positive. The formula shown is sensitivity equals A divided by A plus C, equivalently the true positive divided by true positive plus false negatives. Specificity answers among truly non-diseased animals what fraction test negative. The formula shown is specificity equals D divided by B plus D, equivalently true negatives divided by false positives plus true negatives. These are conditional probabilities based on the true disease status defined by the reference method. That's why the denominators sit within the disease and non-diseased columns. Clinically, high sensitivity is valuable when missing disease is costly, screening, and early detection. High specificity is valuable when false positives trigger harm, cooling decisions, trade restrictions, or costly confirmatory workups. An important implication follows. Sensitivity and specificity can be high, yet the practical usefulness of the test in the field can still be poor, especially if disease prevalence is low. That is not a contradiction. It simply reflects that sensitivity and specificity answer a different conditional question than clinicians usually need. The key point is not memorizing formulas. It is knowing what question each one answers and which margin of the 2x2 table supplies the denominator. Using the BVD table, sensitivity is straightforward. 95 true positives out of 100 diseased animals, giving sensitivity equaling to 95%. Specificity, it's also 95% because 285 true negatives out of 300 non-diseased animals are correctly classified. The interpretation is important. These values summarize test performance against virus isolation in this study setting. They are often treated as fixed characteristics of the test kit, but they can still vary with disease stage, sample quality, and spectrum of cases included in the evaluation study. This is also the right moment to clarify a frequent misunderstanding. Knowing sensitivity and specificity does not directly tell you the probability that an ELISA positive animal is truly infected. That is a predictive value question, and predictive values are where prevalence enters powerfully. Predictive values answer the decision question clinicians actually face. Positive predictive value asks, if the test is positive, what is the probability the animal is truly diseased? The formula shown, its positive predictive value equals A divided by A plus B, or true positives divided by true positives plus false positives. Negative predictive value asks, if the test is negative, what is the probability the animal is truly healthy? The denominator uses all test negatives, so negative predictive value equals D divided by C plus D, or true negatives divided by false negatives plus true negatives. The key statement is that predictive values are highly dependent on prevalence. That means positive predictive value and negative predictive value are not stable kit characteristics. They change when you move from a high-risk herd to a low-risk surveillance population. This layout makes the conceptual shift clear. Sensitivity and specificity condition on disease status, columns. Predictive values condition on test result, rows. That single change explains why prevalence affects predictive values but not sensitivity and specificity. This is also where interpretation becomes more realistic. A positive result is not automatically case confirmed. It is a probability statement that depends on how common disease is in the group being tested. That is why screening low-risk populations can produce many false alarms even with good tests, and why confirmatory strategies exist in program design. The same ELISA is now applied to two different epidemiological contexts, keeping sensitivity and specificity 95% fixed. In the higher prevalence herd, prevalence is 25%. Testing 400 animals yields 100 diseased and 300 healthy, consistent with the earlier table. Positive predicted value becomes 95 divided by 95 plus 15 equals 86%, and negative predictive value becomes 285 divided by 5 plus 285 equals 98%. Both are strong because disease is relatively common. Then the setting changes to a low prevalence herd of 1%. Testing 1,000 animals yields 10 diseased and 990 healthy. True positives become 10 times 0.95 equals 9.5, but false positives become 990 times 1 minus 0.95 equals 49.5. The positive predicted value collapses to 16%. That means most positives are false alarms. This is the central surveillance lesson in low prevalence settings. Specificity dominates positive predicted value. When a survey is conducted, what is observed is the parent prevalence, the proportion of the sample that tests positive. The relationship shown is the parent prevalence is to A plus B above the total, meaning both true positives and false positives contribute. If the test is imperfect, apparent prevalence is biased away from the true value. The Rogin-Gladden adjustment is presented as the correction for this bias when sensitivity and specificity are known. The formula is true prevalence equals apparent prevalence plus specificity minus 1 above sensitivity plus specificity minus 1. The adjustment becomes crucial when apparent prevalence is low and specificity is less than perfect, because false positives can dominate the observed positives. Conceptually, this is the bridge between raw survey outputs and meaningful estimates of disease frequency in the population. The same concept is now anchored visually to the 2x2 table. Apparent prevalence is tied to the test positive row, total A plus B over the full total. True prevalence is tied to the diseased column, total A plus C over the total. The yellow box shows that it's the adjusted true prevalence formula, linking the survey result back to sensitivity and specificity. This view helped prevent a common mistake, assuming that percentage positive tests equals prevalence. In field surveillance, even small imperfections matter because the denominator is large and false positives can accumulate quickly. The table also reinforces the logic that sensitivity and specificity describe the test, while apparent prevalence and true prevalence describe the population. The adjustment is essentially translating from the measurement scale of the test to the epidemiological scale of the population. This is exactly the kind of thinking needed when interpreting surveillance results for programmed decisions where overestimating prevalence can trigger unnecessary interventions and costs.
A realistic surveillance scenario is used in a low-risk region. 5,000 cattle are screened and 75 test positive. Apparent prevalence is therefore 75 divided by 5,000 equals 1.5%. The screening test is strong but not perfect. Sensitivity 98% and specificity 99%. Applying Roggen-Gladden, the true prevalence is 0.52%, not 1.5%. That is a major correction driven largely by false positives accumulating in a large low prevalence population. The EpiToolbox calculator and displayed confidence intervals reinforce that these are statistical estimates with uncertainty, not single truth values. The program implication is immediate. Policy based on apparent prevalence alone can seriously overestimate disease burden and misdirect resources.
The plot provides a visual summary of what the Roggen-Gladden correction is doing. Two estimates are shown. Apparent prevalence around 0.0 for FATIF and true prevalence around 0.005, each with a horizontal 95% confidence interval. The separation between the 2 points is the cost of imperfect specificity in low prevalence surveillance. The confidence intervals matter. They remind us that prevalence estimation is not just about point estimates. It is also about precision. Even when the corrected true prevalence is low, uncertainty may still be substantial depending on sample size and the distribution of positives. In surveillance reporting, it is better practice to present both the apparent prevalence and the corrected estimated along with uncertainty and to explain why they differ. That transparency prevents misinterpretation by decision makers who may otherwise assume test positives equal cases. In addition, low prevalence magnifies the impact of false positives, causing positive predictive value to collapse even for high-quality tests. This reality underpins the distinction between screening and confirmatory testing. Screening aims to capture potential cases accepting false positives, while confirmation aims to establish diagnosis with high certainty. Confusing these roles leads to inappropriate use of tests and inefficient control strategies. Many diagnostic tests produce a continuous measurement rather than a binary label. ELISA, T3s, blood pressure, biochemical markers, none of these are naturally positive or negative. A cutoff is therefore a classification decision imposed on continuous biology. The key trade-off is stated clearly. A lower cutoff makes it easier to classify a sample as positive. Sensitivity increases because fewer diseased animals are missed, but specificity decreases because more healthy animals cross the threshold. A higher cutoff does the opposite. Specificity increases, sensitivity decreases. There is no universally correct cutoff. The correct cutoff depends on purpose. Screening for an exotic disease prioritizes sensitivity. Missing disease is unacceptable. Confirming disease before cooling prioritizes specificity. False positives have high costs. The point is that cutoffs should be treated as programmed decisions, not as arbitrary laboratory defaults. Once this is understood, receiver operating characteristic analysis and Uden's J become tools to formalize and justify those decisions. Receiver operating characteristic, ROC, curves provide a comprehensive way to evaluate diagnostic tests that produce continuous or ordinal results. By plotting sensitivity against 1 minus specificity across all possible cutoff values, the ROC curve visualizes the full range of trade-offs between false negatives and false positives. Each point on the curve corresponds to a specific threshold, making the curve a map of potential decision rules rather than a single fixed choice. The area under the curve, AUC, summarizes overall discriminatory ability, representing the probability that the test correctly ranks a randomly chosen diseased individual higher than a non-diseased one. An AUC of Dirov indicates no diagnostic value equivalent to random classification, while an AUC of 1.0 reflects perfect discrimination. Importantly, AUC is independent of disease prevalence, making it especially useful for comparing tests across populations and study settings before operational cutoffs are defined. Selecting an appropriate cutoff is a critical step in applying diagnostic tests in practice. Uden's J statistic defined that sensitivity plus specificity minus 1 identifies the cutoff that maximizes overall correct classification. This point represents the greatest vertical distance between the ROC curve and the diagonal line of no discrimination. While Uden's J is statistically attractive, it implicitly assumes that false positives and false negatives carry equal weight, which is rarely true in real-world settings. In screening programs, missing infected animals may be more costly than generating false positives, favoring cutoffs with higher sensitivity. Conversely, confirmatory testing prioritizes specificity to minimize unnecessary interventions. Therefore, Uden's J should be viewed as a reference point rather than a rule. Effective cutoff selection requires integrating epidemiological objectives, disease context, resource availability, and the downstream consequences of diagnostic error. Agreement and accuracy are related but fundamentally different concepts in diagnostic evaluation. Accuracy refers to correctness relative to the true disease status, whereas agreement describes consistency between tests or observers. High percent agreement can be misleading, particularly in low prevalence settings where most observations fall into the same category by chance alone. For example, two tests may agree frequently simply because most animals are disease negative, not because the tests perform well. Cohen's kappa addresses this limitation by adjusting observed agreement for the agreement expected under random classification. Cohen's kappa ranges from 0 to 1, with 0 indicating agreement no better than chance and 1 indicating perfect agreement. Intermediate values are often labeled as fair, moderate, substantial, or excellent, but these benchmarks should be applied cautiously. This correction provides a more informative measure of concordance, especially when prevalence is skewed. However, kappa does not measure diagnostic accuracy and should not be interpreted as such. Agreement metrics are most useful when assessing interchangeability of tests or observer reliability rather than their ability to correctly identify disease. When diagnostic tests produce quantitative measurements, agreement can be adequately assessed using correlation alone. Correlation measures association, not equivalence, and can be high even when systematic differences exist between methods. Bland-Altman analysis addresses this by examining the differences between paired measurements plotted against their mean. The average difference represents systematic bias, while the limits of agreement describe the range within which most differences are expected to fall. This approach makes both bias and variability explicit and directly interpretable. Bland-Altman plots are particularly valuable when evaluating new assays, instruments, or laboratory methods intended to replace or align with existing standards. Rather than asking whether two methods move together, the analysis asks whether they produce sufficiently similar values to be used interchangeably. This distinction is crucial for clinical decision-making and surveillance consistency. This summary brings together the core concepts underpinning diagnostic test evaluation. The 2x2 table provides the structural foundation from which all key measures are derived, including sensitivity, specificity, predictive values, and prevalence estimates. Formulas offer transparency, but interpretation must always be guided by context rather than mathematics alone. Sensitivity and specificity describe intrinsic test behavior. Predictive values reflect real-world meaning, and cutoffs determine how tests are operationalized. Agreement metrics address consistency, not correctness, while methods such as ROC analysis and Bland-Altman plots support informed comparison and implementation. The central principle is that diagnostic tests support decisions rather than reveal absolute truth. Appropriate use requires aligning test choice, performance metrics, prevalence, and acceptable error with clearly defined epidemiological and clinical objectives. In the next session, we will build on these concepts to see how diagnostic tests are combined and applied in real surveillance and control programs. See you next time.